Nah, yeah, the blue color we don't. The blue and yellow. I have to tell them it's not that.
Oh, well,
You
why
have
do I,
to,
do I have to
so you need to.
cover?
We
Yeah.
have a policy, you know, the yellow and blue color and the M, the Ohio State, you know, they don't really work well. So make sure to tell them that you're not from University of Michigan.
Ah, I see.
Yeah, they already have the X, right?
I can fix it. We can put an echo.
Yeah, I don't know if you haven't had the time to stroll around, but if you look on campus,
No.
every.
He bought it for
sign,
me because he was.
So they have an M on it. there is an M.
Yeah. He's like, I can take this anymore.
Yeah.
I was thinking something
Yeah,
similar. So people who have a negative reaction.
Go fun.
I make sure.
But
I make sure I'm not in the introduction. Oh, nice. Probabile. Mi ha detto il corso non c'è una focaccia di Recco. Oh, che fortuna. Oh, buono, sì. Pieno sbombato di formaggio e olio. Ah, sì, no, è una roba proprio piena. Io non l'ho mai mangiato.
Di pieno.
Sì, sì.
Vabbè, ma li fa.
Sì, no, l'ho mangiato una volta.
Vabbè, ma è formaggio fuso.
È formaggio.
Forgot to do that?
Yeah.
Are you going to that though when you're
And
there?
they told me that they're taking me to lunch at a place.
It's
I don't know, but
it's
it was
intense.
spelled.
Oh.
And they blah blah blah.
I would eat it. I had a suggestion, but it's in Ricardo.
It's a focaccia with a lot of cheese.
Mi piace la focaccia di Lecco.
Oh.
I think it's that was Silvia.
Wow.
It was probably after
She clearly is not from Genoa.
Silvia not from Genoa?
You cannot make that type.
Boh. Hai visto cosa è
Oh, nice.
I actually don't know.
It's she's
Clearly have a very international
Veramente
collaborations here. Right. I think we do have people online too. I'll wait for the, it's like the orchestra cannot start without Giorgio giving the 1, 2, 3, 4. Yes. Right? We need the maestro
or Polly.
or Patty.
Oh,
Yeah.
what's that? We usually give them a minute or two grace and stuff.
Yeah. I thought you were coming to open the door and announce the entrance of.
Oh,
And now all rise for the honor roll.
Totally, it was kind of like, we were just talking about, we don't start until the maestro gives the 1, 2, 3, 4, and then you came right at that moment. So, anyway, do we have anyone online?
yes. And I will bring any questions over.
Oh, wonderful. Here.
So you can love.
Yeah. Okay. Forgot all of this. Yeah, I used to be the chair for the seminar series and so on. I left and Stephanie's
No, people do that.
before. Oh, yeah. Oh, yeah, that's right.
For the car?
No, the department. Yeah. We have a usual seminar here every week. And then with the department, we bring in some speakers. Because in the weeks that we don't have external speaker, usually the other students, the research staff, and so on use this as a practice opportunity. Pretty busy. Sometimes we have to double teams. But in the starting, especially like during spring when there is like a dissertation or defense.
Yeah.
Yeah, we use this as a point.
Is that the new buildings?
Yeah. Yeah. I think they were probably Georgia was pointing it to you through the doors. Yeah. Testing facility.
That's fast, just one year, 6 months.
Yeah. Yeah. Really quick. It's pretty simple. All right, excellent. We were kind of saying we're waiting for the director to give a 1, 2, 3, 4 to the orchestra. Okay. There we go. All right. Good morning, everyone. Hope you all had a good weekend. It is my greatest pleasure to be introducing the seminar speaker today for our research seminar series. Professor Ricardo de Castro from University of California, Merced. Disclaimer that yellow and blue M, it doesn't have anything to do with the school up north. So please save your eggs and your axes for
rotten
That's a
tomato.
different shape.
exactly. That's a different shape too. Okay, so
And it's a different yellow and a different blue too.
don't put the red sticker on it. Okay. So Ricardo received his master and PhD in electrical engineering from University of Porto in Portugal. And then he had professional experience with the German Aerospace Center, DLR, Institute for System Dynamics and Control, before he became a tenure track assistant professor at the University of California, Merced. And I'm sure he will talk about where it is and all of the good things around it. Ricardo is well known for research in optimization and control of electrification, autonomous vehicle, and sustainable transportation. He has been very active with IEEE in publications, in conference organization. He's associate editor for transactional vehicular technology. IEEE Access has received a number of awards. And is the president for motor vehicles at the IEEE Vehicular Technology Society, founding chair of IEEE Automated Vehicle Standards Committee, and has been the general chair for the 2022 IEEE Vehicle Power and Propulsion Conference. As some of you probably know, he's also the faculty advisor for the Battery Workforce Challenge team at the UC Merced. And with that, I would welcome Ricardo to Ohio State and looking forward to hearing your seminar.
Thank you, Marcello, for the introduction. Thank you all for the kind invitation to be here today and talking about the research. So before talking about the topic, I want to give you a bit of an overview of what we've been doing in the last 20 years. So as Marcello mentioned, originally I came from Portugal, that's where I got my education. After finishing my undergraduate degree, I decided to create a startup with a few of my colleagues. And so this was 2006, and we developed the first generation of motor controllers for EVs in 2006. It was 20 years ago. Unfortunately, the market for EVs at that time was very small, and as many startups, we went bankrupt. So afterwards, I decided to go back to the university, pursue a PhD. There, I had the chance to work on my second vehicle, as we call it, microcar. It was red from the outside, but green from the inside. And we were working with batteries, pre-lithium batteries. So the mass was very high. And during this time, I was looking into hybridization between high energy batteries and high power supercapacitors. Afterwards, I went to Germany. And as Marcello said, I worked a few years in the German Aerospace Center. The core business of DLR is space exploration, satellites, but they also have interest in bringing space technology to Earth applications. And so I was part of this program for 8 years. And there I had a chance to develop my third electric vehicle. We call it the road mobile, robotic electric vehicle. And maybe a video to introduce this prototype that we built during my time there. So it's electric, has lithium batteries. One unique aspect of this prototype was the propulsion. So each wheel had its own motor, pump motor. We also had a steering actuator that allowed the wheels to rotate up to 90 degrees. We also had brake-by-wire actuators, semi-active dampers. Let's see if I can fast forward. So here you can see the animation of the propulsion. So we have four of these actuators in each corner of the car. We could rotate each wheel 90 degrees, so it was very easy for parallel parking. And also another unique aspect of this prototype was the interaction with the user. So there was no steering wheel. We were using a force feedback side stick. So if you are used to operate or if you are used to play computer games, it was very easy to use this vehicle. And you can see here some of the operating modes of this car. We could rotate sideways, rotate on the spot. And the idea of this vehicle was to deploy it in urban environments where it's where the space is very tight. And simulations. In terms of perception, we were using 18 cameras on top of the vehicle for the perception. And so we had different operating modes for the vehicle, manual, semi-autonomous, and autonomous. And one of the coolest things you could do was obstacle avoidance and exploiting this for the steering. You can leverage the car mode to quickly perform avoidance. And also the parallel parking was really nice. So if you struggle with parallel parking like me, you can just plug in and do some great. So this was my life before coming to America. So I was having fun with these prototypes. So then in 2021, I came to California, and then I had to restart from scratch. So I didn't have access to this kind of infrastructure. And so I decided to pivot a bit my career and looking more into the transportation aspects. And when I went to California, I realized that the state is at the high risk of natural hazards and natural disasters. And one of the highest risk is wildfire. You can see here many areas in the state that have very high risk of wildfire. In fact, more than 4 million people live in close proximity to this danger. And then when wildfire occurs, often the local officials they need to ask people to leave their homes and seek a shelter. Probably you heard what happened last year in LA. I live in Merced, it's close to Mariposa in the Sierra Nevada, and every summer there are evacuations due to wildfires there. And the largest evacuation that happened before it was in 2007 in San Diego, where more than 500,000 people had to leave because of the witch fire. And it's not just wildfires, there are floods. For instance, there was a big incident before I came to the US, the Orobi Dam, where it failed. They also had to evacuate more than 180,000 people. If you go to Santa Cruz, there are tsunami problems, there are the risk of earthquake. Some of my family lives in Florida, and in the summer, with the thunderstorms, they are always concerned. And so I started to look into these risks and, okay, if we are driving an EV, how can we be prepared to deal with these evacuations? How can we plan for these scenarios? So I have here this diagram that illustrates the main components that you need to consider during the evacuation. So imagine that you have a hazard or fire that is affecting or threatening the zone. So the local authorities ask the people that are in this red zone to evacuate. Most of them use their personal car for the evacuation. they need to deploy the transportation network to reach the shelter. If they don't have enough energy to reach the shelter, they need to stop for refueling or for recharge. And so if you're looking into the EV charging, and you also need to consider where does the energy comes from for the evacuation. And so you look into generation, transmission, which can be also affected by the natural gas. And when I started looking into this, I was particularly interested into the EV aspect. And so understanding if we are ready to deal with these evacuations, if everybody is traveling. Why is that? Well, in California, 39% of the greenhouse gas emissions are generated by transportation. There is a mandate 4 years ago that sets the goal of selling only EVs by 2035. I don't know if this mandate still holds, but that was the intention of the government. And then when you talk with the state agencies, they have all these nice projections of right now we are selling 35% of new vehicles with battery, but the goal is to reach 100% in the next 10 years. So you fast forward 10, 15, 20 years, you have to deal with the evacuation, and the question is, are we ready to deal with this evacuation if everybody drives it? And so what are the challenges that appear when you're doing an evacuation with EVs? So one challenge is related with the charging time. So if you only have access to level 1, it might take like up to 2 days for you to charge your which is too slow during the emergency. You can use level 2, you can use DC fast charging, but it's still difficult to compete with gasoline where you can recharge. Because of these long charging times, there are concerns about congestion in charging stations. There's also concerns about power outage. For instance, I live close to the hills, and during summer, it's very common for the power utilities to turn off the energy to prevent ignition of fires. So what should you do if you are asked to leave? You have an EV, but the energy in EV, neither energy in the grid. You're in trouble. There's also traffic congestion that affects any kind of vehicle that you use. And last year, there was also this incident that the fires in LA also raised awareness for the risk of the EVs that are left behind. So these EVs, if they have batteries, if the batteries catch fire, that those fires are more intense. They also release chemical contaminations that are much more difficult for the cleanup of fire. So we also need to think about the best practices to deal with these EVs. Great. So with this background, I would like to tell you more about 3 topics of my research. So one is related with the routing of traffic during these emergency cases, taking into account the constraints, charging constraints of EVs, and also looking into leveraging mobile charging units that can support the fixed charging infrastructure if this infrastructure is affected. So where should we deploy charging units? Then in the second part of the talk, I'd like to show you some control algorithms that have been developing to reduce the time for charging of battery EVs, which is important not only during your normal day-to-day operation, but also during emergencies. And finally, if time allows, I'd also like to touch on the recent work we've been doing related with deployment of mobile robots to prevent wildfires. I prefer to prevent the evacuation. So that's the third topic. Okay, so let's now look into the planning setup. So I assume that there is given area that is at risk of natural hazard. There is an evacuation zone, and I collect requests from the people that want to leave. So when do they start? Where do they want to go? What is the initial range, driving range that they have available? And then we collect all these evacuation requests, and our goal is to recommend a route for these people, such that they can reach the shelter as fast as possible while taking into account energy constraints that you might have in there. And also at the same time, we want to prevent congestion in the roads and also congestion in traffic in the charging stations. Typically, this problem is transportation engineering. So as I mentioned before, I'm an electrical engineer. So how do I start looking into this? I realized that in the last 20 years, I've been routing electrons in circuits. And so in the transportation, what you move is vehicles. In the circuits, what you move is charge. When charge is moving, you have current. In the transportation side, when you're moving cars, you have fluid. Also, if you talk with transportation engineers, they tell you about the flow conservation. If you have multiple lanes joining, the summation of flow can be needed with the solution. We call this electrical engineering Kirchhoff's current. Also, when you start looking into the fundamental relationships that connect the concentration of vehicles in a given road link and travel time, you see that there are many similarities between these macroscopic relationships. And in reality, the flow plays a role, or the current plays a role of flow. The resistance can play the role of travel time, and voltage can play the role of vehicle concentration, a number of vehicles that you have in the vehicle. And so at the end of the day, you can implement this using nonlinear resistors. Often you don't want to spend too much time traveling in that road link, so you want to limit the concentration of vehicles, or in the electrical analog, you want to limit voltages and currents to prevent failure. So that's how I understood this problem with my electrical engineering background. Great. So let's then move on with the setup. We have the nodes, transportation nodes that become electrical nodes. To model the time I lose traveling from one node to another, I add resistors to each link or branch. I also add switches to these links because I'm interested in the routing of traffic or routing of current. So I introduce switches to have this option to decide where current or flow goes. I may need to stop for recharging. So how do I model the stoppage time that I lose? Well, I add another resistance. And I also add a special switch, single pole, double throw, that indicates if I stop for charge or not, or I bypass. And then at the end, I also need to include a few current sources. One terminal of the current source indicates what is the origin of the traffic, and the other terminal indicates where the traffic goes. And so through this analogy, the end goal is to find the sequence of switches that minimizes the total resistance between the origin and destination. So in other words, find the path of least resistance, which I've been doing, electrical engineers have been doing for a long time. Great, but that's not all. With an electric vehicle, you have constraints in terms of driving range. So to capture that constraint, we created a second dual circuit. In this second circuit, we use voltage as proxy for the state of charge, or proxy for driving range that you have. So we have the same structure, the same nodes, the same branches, but now between two nodes, I connect a voltage source that mimics the loss of range that I experience when I go from one node to the other. So there is a voltage drop that represents a loss of driving. If you stop for recharge, there is going to be an increase in potential, and so you gain energy during this moment. And so at the end of the day, what you want to do is guarantee that the voltage in all these nodes is positive, such that you have enough energy to reach your destination. Great. So we have our equivalent circuits for driving time, for driving range. In order to figure out the sequence for these switches, figure out the route, we connect this with an optimizer. So the overall goal is to minimize the travel time for everybody. And we have a bunch of constraints that comes from the application of KVL, KCL, the nonlinear Ohm's law, and also a bunch of constraints to prevent traffic in grids. This can be mapped into a mixed integer dynamic problem and that's all with mature. So let's see how this works in practice. I created a use case for Mariposa. Mariposa is very close to Yosemite National Park. So there's lots of forest around the county. And together with the local officials, we came up with this use case where we assume that there is a wildfire affecting downtown. And we selected a couple of shelters where people can go. So in our framework, what we do after defining this use case is to build this equivalent circuit. So you can see here the current sources that are injecting current in downtown. So emulating the traffic that appears during this scenario. And then you have the grounds that are connected to the destinations. Then you have all the resistors and switches that capture the travel time. We then figure out the switching sequence using optimizer, and then we assess the performance of this evacuation strategy using traffic simulator. We did some comparisons between different evacuation strategies. So one strategy is nobody cooperates, everybody tries to follow the shortest path to get to the ship. Then we have another approach, I would call it joint evacuation, where everybody cooperates and everybody follows optimal path. So it's the best for everybody. And then we also looked into an iterative evacuation scheme where we rank all these evacuees based on proximity to danger. So the folks that are closer to hazard, they have priority in accessing the transportation network and also priority in accessing the charging network. And that's the last. So here's some results that we got from Mariposa, and we evaluated this in Sumo, which is a traffic simulator. So you can see here the average travel time. In the horizontal axis, we have 3 of the evacuation groups. So the group here on the left is called the danger. In blue, you have the time when people do not cooperate. And then in orange, you have the joint evacuation planning that provides the best time for the average of all the groups. And then you also have in green the iterative evacuation planning, which is very good for the folks that are close to danger. But then as we move away, you need a bit longer evacuation time. Also, if you look into the routes, the uncoordinated, everybody follows the same path, so there are congestion on the road. And then with these optimization-based schemes and more diversity of paths, so you are more smart the way you route traffic, and they can make a difference if you need to quickly. Then we also did some sensitivity analysis, and for instance, look into what happens if you change the initial state of charge. So you have here the average evacuation time as a function of the initial SOC, and the trend that you see is that you need less time if you have a higher state of charge. That means you don't need to stop for recharging. And when I share this with the local officials, they like this very much because for them, they can come up with a communication campaign to tell people, hey, if evacuation is likely, make sure your state of charge is high during this period. So it's a very effective strategy to prepare people for this. Then another analysis that we did was to investigate what happens if you change the charging rate and travel speed that you have in the network, and what is the impact in the overall clearance time, the time you need to evacuate everything. And so the trend that you see, I think, is also makes sense. So if you can drive faster, you can charge at higher rates, you need less time. But more interestingly is for us to look into these level curves. So imagine that you are a local planner and you have a certain goal, like I want to evacuate this community in 15 hours, for instance. So if the travel speed in your community is low, then it might pay off for you to install fast, very fast. On the other hand, if you're in a community where the travel speed, like in a rural environment, where the travel speed is higher, then you don't need such high charging towers. So this provides like a trade-off for the city planners to understand where they can put the effort and the resources. Great. So now let's look into another dimension related to the loss of power in the charging, fixed charging infrastructure. So if you are evacuating and you go to a fixed charging station, this charging station is not available, what should we do? So we've been looking into deployment of mobile chargers. So these are chargers that have energy storage. They have wheels, so you can very quickly and easily redeploy them in the area. They can provide level 2 or DC fast charging. In terms of storage, there are batteries, there are hydrogen, there are propane. There are like dozens and dozens of companies out there that are building these chargers. And so when we start talking with our local partner, they asked us, okay, great idea, but how many of these mobile chargers should we deploy? And where should we deploy them during these emergencies? Okay, so we went back to our electrical analogy. And so we had to extend our model with these mobile chargers. So what we did was to look into these candidate locations for the deployment of the chargers. So we added a resistance and another switch to indicate if we use this mobile charger. And then we also extended our optimization framework in order to manipulate this additional degree of freedom. Great. So coming back to the Mariposa use case, we could look into what is the impact of adding these mobile chargers. So we are here in the vertical axis, the time that you need to evacuate, horizontal axis, and then the mobile chargers. And we looked into two scenarios. So the blue is everybody drives the same EV with the same battery. And we looked into the heterogeneous case where there is some variability in the size of the battery. But no matter what type of scenario you look into, the trend is as you add more mobile chargers, the evacuation time goes down, and then it saturates around 4. So this information is useful for the community to understand how many of these units they should buy and also where to deploy them. And then we also did a comparison between this optimization-based placement and routing versus a baseline that is provided by IMSA, which is a traffic simulator. And essentially what happens is that with this optimization scheme, you're able to redistribute the people among different chargers. So then you avoid queuing and wasting time during the evacuation. All right, so I'm going to conclude the first part of my presentation. So in summary, we have been exploiting these controllable equivalent circuit models for transportation purposes. So they are able to capture travel time, charging time, and also guide the placement of mobile chargers. We've been also looking into optimization-based schemes for the routing, and also iterative schemes for planning the evacuation. And we deploy these tools in the real world, in this case, in Mariposa, that allows us to get insights into the electric transportation during these scenarios. I would like to point out that this research has been carried out in cooperation with many other colleagues in California, including UC Berkeley, UC Davis, and Davis. We also have many community partners that are involved in the project, mentioned from public officials from Kansas and Merced County. We also have nonprofit organizations, Start, also somewhat involved in EV partnerships, so they bring the user perspective to this. And we also have a few companies that are developing mobile chargers, and they have a lot of interest in this particular use case, and so they want to understand the requirements and specifications. So they're also part of this. And I'd like to publicly acknowledge this financial support we got from state, in particular California Climate Action Grants. Just to finish on this topic, I also will say a few words about some of the feedback we got from this community partners about all this research we've been doing. For instance, an interesting insight they asked about the mobile charging is that if you, for instance, deploy a mobile charger that generates emissions, then you need a permit from the state. That's a barrier. So there are lots of interesting public policies around this topic. Also, emergency routing. In this work, we only looked into routing of private vehicles, but there's also medium duty vehicles, heavy duty vehicles, also need to be routed. So we need to extend that to deal with those type of vehicles. And then when you talk with real people that are doing evaluations, what they tell us is we have no idea how to plan this for EVs. So they don't know the best practices for evaluation. So I think this kind of insights and knowledge we are creating help them better prepare for this. Good. So now I'd like to transition to another topic that is focusing on fast charging of battery EVs, which is important because you don't want to waste time in the charger during these evaluations. So at high level, what is the goal? So we have the battery of the EV. We assume that we have some sensing from the battery, usually temperature, current, voltage, and we want to come up with a charging protocol such that we can go from certain initial SOC to some final SOC, while taking into account a bunch of safety constraints. So you have electrical constraints, voltage, current. You also have temperature constraints. There are elements inside of the battery that are very thermal sensitive, and you don't want to go with very high temperature. There's also lithium plating, which is lithium that is deposited in one of the electrodes, and it can grow, it pierce the separator, creating short circuits. And so we want to come up with a charging protocol using controls that deal with all these requirements. So if you look into literature, there are at least three main branches to solve this problem. One branch is more like heuristics, where people use, constant current, constant voltage. There's also pulse charging that is gaining popularity in the last years. There's also reinforcement learning using data-driven approaches. And then you have model-based. The holy grail has been MPC, control. We also have installers. And in my group, we've been investigating for the last 3 years methodology control barrier function, which are very popular these days in literature. And so trying to apply these CBFs to fast charging problem. Why CBFs? They are able to enforce the constraints while having less computational effort versus other like MPC as well. So these are model-based, so we need a model. Guess what? Here, I'm going to use circuits to model the pattern. One technicality here is that we are using an electric circuit that is composed of two circuits. So one circuit for the anode, another circuit for the cathode. And this allows us to predict what is the voltage of the anode. And if that voltage in the middle here, third terminal, goes below zero, these are conditions for everything. We want to prevent that voltage from becoming. So then that's the model for building the method charging protocol. We need to specify a bunch of upper limits that we don't want to exceed, temperature, voltage, you name it. So in the control barrier function, what we normally do is to map each one of these inequalities into a super level set. So essentially, we build a function here in this slide called C that measures the distance to the boundary of your safe set. Okay? So if you're at the boundary, this C is 0. And if you are violating the boundary, C is negative. So when you are building these CBFs, what you want to do is to limit the speed at which you are approaching the boundary. And if you violate the boundary, then you want to have higher speed to bring the state back to state. So in this CBF approach, essentially what you are doing is just introducing a bound on how fast you are pushing the boundary, and then you can map these bounds into a set of control actions that enforce. So we apply this to the battery, and what we are doing here is we have a bunch of constraints, and we are monitoring at each time instantly monitoring what is the maximum current I can apply such that I don't violate the law. What is the maximum current I can apply without violating? What is the maximum current I can apply without violating any of these constraints? So when you look into the animation, we have all these possible currents, safe currents that I can apply, and then at the end of the day, I just apply the minimum of all these safe currents, which is going to fulfill all the safety constraints. And so then we apply these experimentally. So we have a small lab in Merced with some tests at the cell level. And you can see here some of the results. So we have here current, temperature, terminal voltage, and SOC. So the objective is to keep all these variables below the red lines. These are the limits. So we start by applying as high current as possible to quickly charge the battery. So then we hit the maximum voltage limit. It can be the terminal or the lithium plating constraint. And then for most of the charging, we are going to operate at the maximum possible temperature that the battery allows until we reach the end of the charge. We also did comparison between these control variables versus the CCCV. We were able to decrease the charging time in up to 24%. We also did some comparisons between the control variable function and MPC. And what we observed is that the CBF is able to provide very similar levels of performance and constraint satisfaction as the MPC. But the main difference is the computational effort that you need. So we're able to decrease the execution time in more than 7 times, which is particularly attractive for the automotive industry, where they want to implement these algorithms on board microprocessors with limited. And what is the next step? So UC Merced is part of the BWC competition. And so we are planning to bring some of these algorithms to the battery. I don't know if we're going to make it, but we're making an effort to test it at the back level. I also want to publicly acknowledge the financial support I got from California Energy Commission, Helmet Foundation, and also to do this research. And if you want to know more about this line of work, there is nice references information to look at. Good. So I have 3 minutes. So I want to now touch very briefly on the last project related with prevention of wildfire using mobile phones. Why? Because I prefer not to evacuate if possible, right? And so what is the motivation for this? So imagine that you have a forest with trees, there's lots of vegetation on the ground. Assume that there is an ignition, this thing catches fire. If the flame height is high enough, it can catch or it can reach the canopy. And so if the canopy is on fire, then these things can propagate very quickly and catastrophic wildfire. So how can we mitigate or prevent the severity of wildfire? So we can try to clean the ground vegetation. And so if there is a fire on the ground, and if you don't have so much, they call it fuel on the ground, then when there's a fire, if the flame height is not high enough to reach the canopy, you have the severity of the wildfire is not as high, and it's also much easier to fight. So how can we get rid of this vegetation? So one approach is using this hand thinning team. So it's a group of people that go to the forest. They cut the branches, they cut the trees with the small diameters that do not have much economic value. And then they do the pile and they do the burn, which is, controversial because of the smoke, and the burn can also get out of control. So what we're looking is to extract this this wood waste to some running site that can be then shipped to some biomass process. But this is pretty time consuming, requires labor. And so we've been developing some robotic approaches to automatize the transport of this slash inside the forest. And so we've been building this platform with four motors, with cameras, with lidars, and with actual trailers that can support and this crew that is in the forest, so they can dump here slash and use this platform to accelerate the extraction of waste. Interestingly, developing a controller for this platform is not that different from developing a controller for a car. So here we have been the first control we developed was to follow the person that is in front of the robot. So we have a controller that monitors the distance between the lead person and robot. So it's kind of a cruise control for this problem. And now we also have a lateral controller to track the lateral motion of the person. And we are also using controller functions for the obstacle. And these are some of the first tests we did in the summer last year. So here a comparison between the robotic assisted, the robot, the slash, and it's following the person, versus the human approach, where you have to carry yourself the wood waste until you reach the levels. And so if you have to do this like for 4, 5, 6 hours in a day, you're going to be wasted very quickly. So I believe that this automatization of these tasks will play a big role in the future for us to get rid of this fuel. And I'm still trying to understand if there will be some economics for these wood waste that we are shipping to the landing site. I think that's all. So I'd like to thank also my team at Inmerset that is helping me in developing these projects. And so thank you so much for your time and attention.
I have to make immediately a comment for business opportunities that work here in Ohio. Robotic assisted snow blowers. I can see people would pay for this immediately, okay?
Thank you so much.
Very nice.
Very nice and very representative. Any questions from the audience?
Siri.
Yes.
I have 2 questions, Professor. So first, when you have this evacuation plan, then let's say somebody takes this plan, the other one takes this plan, right? Now, at some point of time, I saw in the graphs that they're merging. But now, how do you model that intersection? Because like generally, if someone is in a traffic jam, they're going to do the zipper merge and behave like normal people. But in evacuation, they're not going to be like that.
Yes, that's a very good question. So right now, testing the results. Here, I'm assuming that people are compliant and that they follow these best instructions that we can give to them. In practice, will they follow this or not? That's a big question. If you want to model that, we can inject some level of uncertainty in the simulations and introduce some level of panic. So we're kind of doing that. I didn't show the results yet, but we're kind of looking into that as well. But right now, what I presented here is in fact, we have 2 extremes. You have one extreme, which is the uncoordinated, where everybody are selfish and they want to get as quick as possible to the destination without cooperation. And then you have the best case, which is this optimization. And so in reality, you are somewhere in between. So this gives you the balance.
And my second question is about the CBF that you had. So now there are going to be some states that move very slowly, like temperature, right? And then there are some states that are going to move faster, like voltage. So do you prefer some states, like some state trajectories over others?
So I would say my perspective on this problem is I'm a control engineer, so I don't know much about patterns. I don't know much as Marcello on the electrochemical models of patterns, so that's not my world. what my perspective is, so the electrochemical engineers, they tell me these are the constraints that I shouldn't exceed. So this is the maximum temperature, this is like the voltage in the anode to prevent lithium plating. This is the maximum current, maximum voltage. I don't know where these limits come from, but I know I need to enforce them. So I need to compute the current, that's the current or the cooling. These are the two tuning knobs that are available, such that I don't exceed these limits. And for where does these limits come from? I'm not the expert there. Okay.
Very interesting presentation and very cool algorithms. So you showed that an heterogeneous distribution of initial state of charge affects the traveling time. And I was wondering, since you perform an optimization algorithm, might uncertainties in the state of charge estimation affect this optimal solution? And is your algorithm robust in this case?
Very good question. So that's a critical assumption. You have some idea about what is the initial state of charge, because depending on the initial state of charge, you might need to take different routes for stopping. So what our approach here was to deal with that using sensitivity approach. So what if your initial state of charge is, if your state of charge is 50%, and then be prepared to deal with all these different scenarios for the evaluation. But I have to say, in practice, that's one of the big uncertainties. Because honestly, we don't know if we are planning this, we know exactly how much charge people have at the beginning. That's going to be a big one. But we solve that through sensitive scenario based.
But also maybe during the traveling path, the energy that it takes might depend on the traffic and on other factors that might affect, in turn, the state of charge. So that's why I was wondering,
I see.
do you account for that? It would be very cool.
You showed the comparison between MPC and CBF. So MPC has CBF constraint or?
No, just the classical,
Without
the
CBF.
vanilla NPC. Just with the regular constraint.
You never bothered to add CBF to it because it was already.
CBF works so well. Why should I be so?
So how do you made the CBF work? Was it MPC with CBF?
No, CBF or NPC.
So it's CBF is a constraint, right?
Yes. So in this case, the set point, the let's say unsafe set point, is to apply as much charge current as possible. That's the trajectory. So that's kind of straightforward. The unsafe set point for the charger.
And you had other battery dynamics in parallel with that as a CBF as a constraint.
So yes, I would say the trick that we explored. So you can try to build a CBF with all the constraints, handling all the constraints simultaneously. And another approach that we've been exploring is to kind of decompose these constraints and then look at one constraint at a time. So imagine that you just want to enforce like the temperature, maximum temperature. So you can build a CBF that focus on this particular problem. So trying to find what is the maximum current that you can apply to the battery without violating the temperature. And then you can do the same like for lithium plate, for voltage. And so you are doing one at a time. And then how can you bring them together? What is the safest current? The minimum. Right? That was the trick. So it's pretty, in fact, I have to say, even the computational times, if I show, are misleading because I can implement these analytically. So the computational times benefits might be.
These are 4 running in parallel, right?
Yes.
4 CBF running.
Yes. Yes. And then if you have, like, let's say that the customer comes back and say, oh, I want to implement this additional feature. And you can add another, yeah, so it's very modular. We have a patent pending on this. We're trying to commercialize. We know some customers happy to chat.
I have a question on the evacuation model. So the scenario, the green scenario, the uncontrolled scenario, you mentioned that you model the individuals as really want to minimize their own travel time. Is that you formulating that as like a game theoretic method?
In the transportation literature, they call this system optimum.
Okay.
Essentially, the assumption behind is that the people who follow this, they cooperate to find a solution that's best for everybody. That means there might be some that we need to take a route that is slightly longer. There are others that are faster, but they accept this compromise. So if they are not willing to accept this, then we need to. So which we are exploring.
Yeah, but I was curious if you're working with the state agencies, you have access to data from prior evacuations that are showing what type of behavior.
It's very difficult. We have these talks with them. What they tell us is like the people like that live in Mariposa, our users, the locals, their mindset is we live here, we know the roads, we know what is the best route to reach the shelter. So they will not follow.
Tell me what to do.
They will not follow the route that I'm telling them. And then you have, again, in Mariposa, they have many visitors that go to Yosemite. They don't know the roads, and they will follow blindly the recommendation I'm telling them.
Fine.
So these are the two people that we need to model together.
Go with that human side, right? There is the behavioral decisions.
So there is the emotional attachment of the locals that make them reluctant to leaving their property until the very last minute and so on, right? It's
True.
That's also a factor that could change the start times of the trade.
True. They have like animals. I think they are rural. They have like horses, animals. And you also need to evacuate them as well. The animals. And they want to wait until the last moment to see if the danger goes away. So it creates also risks. So it's a
Very rich subject to mind for research, actually. Very cool.
and you can save lives, right? So if this ended up being deployed, it's real.
That's societal impact, yeah. Any other question for the speaker?
I have a question, and it might be a lack of understanding, so I apologize. When you look at the initial state of charge for the evacuation, I'm a little confused how that feeds into the evacuation plans, because I'm trying to picture a situation where there's a few irresponsible people, not from experience or anything, who forget to plug in their EV, and I'm thinking that would pretty dramatically affect the congestion. Even if you have like a very small subset that runs out of power 5 miles in, is there a way to account for that in the way you've set up the evacuation plans, or it's not really there?
So when it comes to the human factor, you need to remember to plug in available experience when evacuation might be likely. So if you're living in Mariposa, you know that in the summer, like July, August, September, there are fires. So it's likely that you might need to evacuate. Every summer, there are evacuations there. So the best way, let's say from a practical perspective, the best way to deal with this is to come up with information campaigns like billboards saying, oh, remember, it's August. Make sure that you have high state of charge in your vehicle because it might make a difference if you need to evacuate. You might be able to reach a shelter without needing to stop for charging. And by the way, the chargers will not be available when you're evacuating. So it's more like, I would say these results that I presented, it's more to motivate the people to create this awareness.
I guess the best way to optimize for that group is just to try and eliminate that group instead of trying to plan around it at all.
Yes, and it's also cheap because, all this, how do you deploy this in practices optimization, right? So
Right.
you also need to convince people to follow these routes. But if you just come up with an information campaign, they already have the infrastructure in place. So when I talk with the officials that are managing these emergency operations, they like this idea very much. So from everything I showed here, this was the ones that, oh, I can do this tomorrow. I can create this information campaign to raise awareness for this. I was surprised, like, oh, I have all these cool tools, all this optimization, that you can save like 1 hour in efficient time. I would like that. Let me see this impact of the SOC. That was the feedback.
I see. Makes sense.
Maybe I might have missed it, but can you tell a little bit more about these mobile charging stations? Are those like common products? Do they
Yes.
use like a diesel engine? How?
All that stuff.
Okay.
All that stuff. But when I started the project, I had no idea. I thought there was only 1 or 2 manufacturers. But then when you go to a trade show, like if you go to this advanced clean transportation, half the show is only like dozens and dozens. They come in different shapes and different sizes. So you have here, this one is a bit smaller. It has like 20 power. It's battery. It can provide up to 5 DC charging. But then this can scale all the way like to a truck level. And if you put like hydrogen or propane, then you have like megawatt power. In fact, some of the companies I spoke with, they are planning to deploy these not for evacuations, but for the Olympic Games
Okay.
in LA. I think it's 2028. And they also are planning to have electrical eVTOL operations during that time. And so how do you going to charge those eVTOLs? You don't have the infrastructure. So we are planning to deploy this kind of mobile chargers for that use case. But then I see, oh, probably I can also sell these to the local authorities that might need to deploy this in case of an emergency.
Yeah, I was speaking of that. I was actually intrigued by the economics of it because I do not imagine them as being cheap.
Yeah, exactly. Yeah, exactly. So that's the same feedback I hear. So who's going to pay for this? So one line of thought is let's go to some of the politicians and see if we can get some public funding to acquire this. Another option is, for instance, mobile charging as a service. Like Mariposa, they know that during the summer, 3 months, evacuation is likely. So probably they can rent this for 3 months out of a year. And then the other option is to kind of pool. So like when you go into these metropolitan areas, you aggregate several communities and more resources. So probably they can acquire this from a given area and then share that.
Right. I think we can thank the speaker once again for. And I don't know if you saw, but there was a delivery person with pizza from Adriatico, which should be waiting in the kitchenette. So please stay, get some pizza, and enjoy talking with the speaker and with us as we carry into the next hour. Thank you so much for coming.